Hello YouTube. Today I'm going to show you how to work an oscilloscope, and this was from special request for me to do this video, and I'm sure not many of you will take a liking to it. You probably already know how to use one, but for those who don't, hopefully this is helpful. So an oscilloscope, let's start with that. An oscilloscope is essentially like a multimeter. You know your standard multimeter. It looks like this. That takes voltage and resistance measurements. Now, the oscilloscope is essentially just that, except that it takes measurements, a bunch of measurements over time, and it's like a multimeter with time, and then it just connects the dots between. So it takes like X amount of samples, takes X amount of voltage measurements over time. So like a multimeter is great for constant value, like power, such as like your VCC voltage or your ground, if you want to check to see if you have a steady ground, or you want to check to see if you have a steady voltage, and you want to see if you're in a certain precise constant value. The multimeter is terrific. Now with the oscilloscope, say you have a data path, something that's going up and down in time, your multimeter is going to be useless in telling you much about that signal, and that's where it comes into play. So it is really used a lot in digital electronics and like sending over data, like I had said before, with different communication protocols. So what I have set up right now to show you how to use it is a simple 555 timer in astable mode, and it's just outputting a frequency. I haven't checked the frequency yet. I just threw a bunch of resistors and capacitors, threw it up in astable mode. So we'll actually find out what the exact frequency is, and we'll find out the voltage that the frequency will be at. I'll show you the signal or I'll show you what I'm talking about. So this is the circuit, and I'll zoom in a little bit for you. So we just got our power. It's a 555 timer, just meaning it does different things. Like it does astable mode, monostable, and bistable. Monostable, you just have one single pulse, and then astable, you have a bunch of pulses. And then bistable, never used bistable, and I'm not entirely sure what that does. I just know it's available for you. Astable is the one that I use most of the time, and monostable has its own unique use cases as well. So right now you have this goes into the oscilloscope, so you can see going right into the oscilloscope here, and this clips on. These are really expensive, so be careful when you're using these. Mine cost me 60 bucks, and it was like the cheapest one they sold, but it worked for my use cases. And then you have your ground. This is the ground clip. In most industry applications, you're gonna have like a little poker instead of the clip, which is nice for like proto boards, like what I've got. You're gonna probably have like a little puncture, like if you take this off. See, it's gonna be like that. It's gonna look like just like that, and then you're gonna have like little ground spring, it's called, and it's just gonna be a spring that's tightly wound, and it's gonna sit on top of this, and then have like, it's gonna come out just a little bit and go forward. So then when you're probing your signal, because on circuit boards you have like your signals, and then you're gonna have grounds next to those signals with high speed cases. So you probe the signal that you want, and then first you get the ground, the spring, which will be on here, and then you put it at the ground via, and then you poke the signal that you want. That way you get a nice solid ground, And that's really important when you're measuring high-speed signals, is to get a really nice ground. Something like this would never fly. The reason being is because you have a lot of switching that's occurring, and that EMI, that magnetic interference, will just come up from the board if it's powered on, and then of course it's going to be, and it's gonna affect this ground, and then it's gonna go into your oscilloscope and affect the ground plane on your oscilloscope, and then you'll be getting false readings. So you want to make sure that you're always using the smallest ground possible. In a use case like this, it doesn't matter, especially since I have nothing switching over here. It's not a big deal. So you can see this is a pretty ugly signal, but it's just for teaching purposes. So you look at this and it's like, oh my god, what are all these buttons doing here? Let me take this out so you can see. So you have all these buttons, right? And you're like, wow, that's a lot. So it's really not that big of a deal. The things you're gonna wanna use mostly are like voltage peak to peak, meaning like from the top to the bottom, that's peak to peak. So that shows you how big your signal is. I know it's hard for you to read what this is, so that's like time measurement. You can do different measurements, which is fantastic. So let's measure voltage. So then you come up with your little window here. This is an old analog scope, which is using like cathode ray tubes. Your digital scope is going to be a lot more accurate. Let me just prop this guy up on its tripod. Okay, it's going to be a lot more accurate and be able to do get you a clearer signal, and it's going to be a lot quicker than this one. But I love this oscilloscope. It does everything I needed to do. So here, VPP, voltage peak to peak. Boom, comes across. It's telling me that my voltage peak to peak is 10.16. So that tells me, and then you can see the cursor. See the cursor, like that just popped there. If I clear the measurement, see the cursor's gone. So this is telling me that it's measuring from the top of this voltage to the bottom. So personally, I don't like that because it's telling me that like over glitch right there at the start. So I want to actually go over here and measure I want to measure this myself. So I go to cursors, and then I have V1, V2. So I do V1. See, I highlight V1, and then I can move V1 up and down using this scroller, and it's going to be the same on the digital scopes. So you move it where you want it, V2, scroll up and down, and boom. Now it's more like it. I got 8.125 volts. I'm using a 9-volt battery, so we know that that 10 volts that we were reading before was actually impossible. This is more like it, 8.125 volts. Alright. Now let's go back to measuring voltage. We can do V average. So that would be 7.358. That's another more realistic. That's taking the average across this signal, and it's also including the downtime as well. Okay. So this is after the duty cycle has been taken into consideration, 7.355. And the duty cycle, it's essentially I believe it's the percentage of the time on versus over the period. I don't know. All I know is it's like a percentage of on versus off. So you have like 50% would be you have on and off, and then like 50%, and then like 70% duty cycle would be like 70% on, and then like 30% off. It makes sense? In one period. Mathematically, that would be like the percentage times the time on divided by the period, I think. So you can just look up duty cycle, you can find that. So if you care. Cursors, time. Cursors are like the really most important because you can just measure different things. So like we can measure the voltage or we can measure the time. So let's do time now. Now we measure the time. So we do like this, and then we measure one period. So let's do, there's one period. And see, 1 divided by delta t, 260 kilohertz. Also, I should let you know that the x is your time. Sorry for the shaking. X is your time, and then Y is your voltage. You can also do current measurements, and that's a lot more complicated to do current measurements with scopes, and this doesn't do current measurements. My scope, so I can't show you how to do that. Alright, and then another important thing to use is a trigger. So the way that works is you trigger it to your scope to turn on at a certain voltage. So you saw those spikes that we were getting as soon as like we would get that swing in voltage from on to off. Remember when I was measuring like 10 volts? So as soon as I turn on my 555 timer, I could trigger it to tell me, hey, oscilloscope, give me my measurement as soon as the signal that I'm sending to you reaches 5 volts. So as soon as it reaches 5 volts, you give me that signal, and then I can zoom in all the way on that signal, and I can see exactly how high it's going and like what kind of spikes we have in there. Once again, on my scope, it's not, I can't get that close, but with a digital one, you can just like zoom right in on that pup, and you can see all like your inductive spiking, because like inductance, capacitance, it's going to be like using like your characteristic equation, which is L over square root of L over C squared, like square root and then in parentheses L over C, and then out of parentheses squared, and then like all that's under the square root. That shows your, and then you multiply that by R, so that shows your current. So like if you're working with voltage, you actually like, you want to, if you wanted to decrease your voltage as soon as it started up, you would want to then increase your capacitance, okay, or decrease your inductance. That's all that is. And you can zoom in on those spikes with digital oscilloscopes. And that's pretty much it. If you have more questions, feel free to ask. It's pretty self-explanatory, but like you just have to get used to like cursors. You have to know what that is, like, and then you just follow the menu. They're really pretty easy to use. As long as you have a fundamental understanding, you can work from there. And okay, best of luck. Wish you all well. Thanks for watching. Bye.